Hello, grade 8. So this week we are starting with chapter 4, which is mechanical waves. Okay, so this is something new and yeah, it's very interesting. Let's start. So you guys will be able, at the end of this lecture, you'll be able to define a wave. You will know the propagation of the wave occurs without the transport of matter. You will be able to distinguish between transversal and longitudinal waves, and you guys will be able to characterize a periodic wave. When I say wave or mechanical wave, what is the first thing that comes to your mind? I know that water waves or sea waves, the waves that we see in water, they are called also mechanical waves. Guys, have you tried, like, I don't know, like throwing a rock in a lake? What would happen? You guys will see some ripples, right? You will see some waves, some circular waves. And if you take a side view look, you would see that the waves look like this, right? So these are the sea waves. We've seen them. Now, of course, we have other mechanical waves like sea waves. We've seen sea waves. Sound waves. We're going to explain this in the next chapter. Seismic waves, which are the waves that happen due to earthquakes, and the waves that travel along the rope. They are all examples of mechanical waves. Now, why am I calling them mechanical waves? Because these waves, they propagate through a material medium. It means that they need a medium for the wave to travel in. The medium could be solid, it could be liquid, or it could be a gas. Okay? So a wave is simply a perturbation which means a disturbance that propagates through a medium. So if you put your hand in water and shake your hand, you guys will see that you are shaking the water, so you will be creating sea waves, okay? Or water waves. Now, one more thing, if you take a look at this duck, what do you notice? So the energy that is being transported by this wave is going this way. See? The energy is going this way. But how about the duck? Is it moving with the wave or is it simply going up and down? I'm seeing it going up and down and it's not moving with the wave. Why is that? Because a wave transports energy. Without the transport of matter, this duck is matter, right? It has a certain mass. It means that it is matter. And see, it is not being transported with the wave. It is only going up and down. And yeah, because a wave only transports energy. Now, not all waves are the same. We have two types of waves, transverse waves and longitudinal waves. So what can you see here is actually a transverse wave. So you guys can see many pendulums, and if you take a look, if you take a top view look, you would see that the particles, which are the little balls, they are vibrating, they are moving. You can see how they are moving perpendicularly to the direction of propagation of the wave. So the wave is moving this way, but the particles are going up and down. Guys, does this remind you of a certain thing? It is like the wave that people do in stadiums, right? When you stand up and then sit down, and then the person next to you stands up and sit down, you create a wave, okay? And this wave is called a transverse wave, okay? It's because the particles are going up and down, so they are vibrating perpendicularly to the direction of propagation of the wave. Now, the second type of wave is called the longitudinal wave. All right, longitudinal wave. Let's take a better look at it. I guess this way we can see it better. You guys can see in the longitudinal waves that each particle is moving like this. So it is vibrating parallel to the direction of propagation of the wave. So it is not vibrating perpendicular, it is vibrating parallel to the direction of propagation of the wave. And yeah, these are the two types of waves. So, as we just said, we have two types of waves. The first one is the transverse wave, where the particle, it vibrates perpendicularly to the direction of propagation of the wave. And if I were to give you an example of this, it would be sea waves, or maybe the waves along the rope. Okay, so yeah, these are all transverse waves. And this is a better, I guess, explanation for it. So you can see, you can hold the rope, okay, and then the up and down motion of the rope is perpendicular to the direction of the wave. So the wave is moving this way, the energy is being transported this way. All right, so yeah. The other type of wave is the longitudinal wave, and this experiment is usually done in class where we bring a spring and just give it a little push, back and forth motion, just like that. And you can see that the energy is being transported. See? So the energy is being transported along the spring. You guys can see that the motion of the particle is parallel to the direction of propagation of the wave, and it is not perpendicular like the transverse waves. An example of that are sound waves, which we will talk about it in the next chapter. And this picture makes things more, easier, where you guys can see the back and forth motion of the coils of the spring is in the same direction that the wave travels. Okay, so the motion of the coils of the spring is in the same direction as the wave. Okay, how the wave is actually traveling. Moving on to the types of motion that we will be dealing with. So first of all, we have the periodic motion. I'm going to talk about two types of motion. So the first one is the periodic motion. Periodic motion. Let me give you an example. So Earth rotates around the sun. Every 1 year, Earth finishes one full rotation around the sun. Okay, so the periodic motion is the motion that repeats itself identically during a constant time interval. So, since Earth every 1 year finishes one rotation around the sun, then the motion of Earth is periodic. Another example, the heart. You can see that the heart is beating. Okay, so is this motion that you see right here, this movement, it is repeating itself identically, the same movement every time, during a constant time interval. So it takes exactly the same time to do the movement again and again and again. All right, so this is periodic motion. It is the motion that repeats itself identically, same motion, during a constant time interval. It takes exactly the same time for the motion to happen again and again. The second type of motion that I will be speaking of is the vibratory motion. So you guys can see from this pendulum that is moving, it is moving back and forth between two extreme positions. Okay, so this is what a vibratory motion is, or we call it oscillatory. So it is a back and forth motion between two extreme positions. Okay, so yeah, let's take a look at this vibratory motion in this simulation. So another vibratory motion you can see using the spring this time and not a pendulum. So I will be just pushing this box. Okay, you can see I'm compressing the spring and I'm gonna let it go now and let's see what happens. So the box is vibrating between two extreme positions. You guys can see between two extreme positions, it is vibrating. Now, if I were to find the time that it is taking the box to go over there and then come back to its initial position, to go and come back, it will take exactly the same time every time. So this is a vibratory motion, but is also periodic. This can give us a conclusion that every vibratory motion is periodic. It repeats itself in a constant time interval, which is the time right here. And actually, we call it the period. Okay, so we call it period, which is capital T. Now, this vibratory motion that we just talked about, which is also periodic, it will create a wave. Okay, let's say you're doing this vibratory motion in water, so you're putting your hand and you're moving your hand back and forth in a constant time interval identically. This will create a wave, a periodic wave. Okay, that looks something like this. So from now on, we're going to schematize, let's say, the wave this way. Okay, so you're gonna see the waves looking like this. We're gonna put it in an axis, XY axis, where the x-axis is usually the time axis or the distance. It depends on the given. And the y-axis is the displacement, how much this wave was displaced vertically. You guys can see the wave going up and down, just like that. And it has some maximum points and it has some minimum points. The maximum points, we call them crests. So these are crests. And the minimum points, we call them troughs. Okay, so we call them troughs. So A and C are crests and B and D are troughs. Okay, you guys need to remember this. This is important. So the maximum point is called a crest and the minimum point is called a trough. Now, the first characteristic of a periodic wave is the period. The period is the time required to complete one oscillation or one cycle. So the wave starts from here, it moves up and down until it reaches this point. And you guys can see, starting from this point, the wave will start to repeat itself. This part, it looks exactly as this part right here. Okay, so for the wave to complete one cycle, this is the one cycle that I'm talking about, the one in red. Okay, so this is the period. This is the period that I'm talking about. Since the x-axis is the time axis, then this is the period. Okay, this is the time it takes the wave to complete one cycle. But guys, what if the wave starts from here? For it to complete one cycle, it needs to reach another crest. So this is also the period. What if the wave wants to start here? Okay, then for it to complete one cycle, this is also the period. And you guys will get exactly the same period. Okay, so as a definition, a period is the time required to complete one oscillation or one cycle. Its SI unit is second. Okay, so it is in seconds. It is time. All right. The second characteristic is the frequency. Frequency comes from the word frequent. Like, does this happen more frequent or does this happen less frequent? See? So we use it in English. And yeah, so the frequency is how many vibrations do I have in one second. So how many vibrations? The number of vibrations, the number of cycles, the number of oscillations that are performed in 1 second. Okay, but how can I know that? We have a simple formula where the frequency, it is equal to 1 over the period. So if I have the period, it means I can find the frequency. It's easy. But the SI unit of frequency is hertz. Okay, so the SI unit of period, it is second, but the SI unit of frequency, it is hertz. H, Z as a symbol. But guys, what if I have the frequency and I'm trying to find the period? It's simple. We just reverse them. So the period can be 1 over the frequency, and that's it. So if the exercise gives you the period, it means you have the frequency as well because you can find it. If it gives you the frequency, it means you have the period because you can find it. Okay, so the frequency is the number of vibrations performed in 1 second. So how can I tell which wave has the bigger frequency? Let's look at these two waves. Okay, so this is A and this is B. Which one has the bigger frequency? B has the bigger frequency. Why is that? Because you guys can see during a certain time, which is exactly the same time right here. Here we have 1 cycle, but here we have 1, 2, 3 cycles happening. 3 cycles performed during this time. So more cycles, more vibrations, it means that this one will have the bigger frequency. You guys get it? Okay. Now, moving on to the number of vibrations, which I just mentioned. It is the number of cycles that the wave produces during a period of time. You can count them. 1, 2, see? So you can count them. Now, there is a relation between the number of vibrations that I have, the time, and the period. So you guys, I can find the period not only by looking at the wave and finding this time. So this is the period usually. No, I can also find it using this triangle because the period is equal to the time over the number of cycles. Also, the number of cycles equals the time over the period, and the time equals to the period times the number of cycles. What is the time that I'm talking about, and what is this number of cycles? I'm gonna draw it here. Let's say I have this wave, okay? So you guys can see this is time, all right? So you guys can see during this time, what if they gave us this time, t? Okay, and I need to find the period. So I have this time and I have the number of cycles that are happening. This is 1, this is 2, and this is 3. I have 3 cycles, and I have the time that it took for the wave to move from here to here. So I can find the period by simply putting t over n. Okay, so yeah, this is the time that we are talking about. The third characteristic is the amplitude. The amplitude is the maximum displacement of the particles from their equilibrium position, which means it is the distance from the crest to the equilibrium position, which is the time axis in this case, or from the trough to the equilibrium position. This is the amplitude. Okay, how about the distance from the crest to the trough? This whole distance. This part is the amplitude and this part is also the amplitude. So this distance will be 2a, right? Because it is double the amplitude. So the amplitude, as I said, it is the maximum displacement of the particles from their equilibrium position. I'm talking about displacement, which means that the SI unit is meter, is how much it is displaced. Okay, so it is in meter. And as I said, the distance between the crest and the trough is double the amplitude. So the fourth characteristic is the wavelength. from the name of it, wave length. So it is the length of the wave. But it is the length of the whole wave? No. Wavelength is the distance covered during one period of the source. I know that this wave is moving. I want to find the distance that it's covered during only one period. This is called the wavelength. But guys, do you notice anything different here? Yeah, so we used to have time here, right? Now I wrote distance. You guys can have two, let's say, exercises, okay? So I can represent the wave with the x-axis being time, and I can represent it with the x-axis being a distance. It depends on what you have. The solution changes. So if the x-axis represents the distance, it means that the wavelength, it's a length, okay, which means that it is in meter. This is the SI unit of it. So it will be the distance from crest to crest, distance from the beginning to the end of a cycle, or I can find it as the distance from trough to trough. You might say, teacher, this is the same as the period. Yes, because it is the distance covered during one period. Okay, during this little time, let's say this is 2 seconds, I'm trying to find the distance that this wave covered during these 2 seconds. Okay, but why did I represent it on the wave right here? Because the x-axis is distance. If the x-axis is time, then I cannot do that. Instead of being able to find the wavelength from the wave right here from the graph, I won't be able to find it. I will be able only to find the period. So if I have time, I'm able to find the period from the graph. If I have distance, I'm able to find the wavelength from the graph. See guys, so you have to look at the x-axis first. If it's distance, so you guys are able to find the wavelength. Okay, so the wavelength, you are able, as if it's given, you can find it from the graph. But if this is time, then instead of finding the wavelength first as a given, you can find the period. Okay, and then of course using the formula in the next slide, you are able to find the wavelength. It's no problem. All right, just as a definition, the wavelength is the distance that the wave covers during one period of the source. So during only one period, how much distance did it, cover? And the last characteristic is the wave speed. Guys, we have a distance and we have time. Then we can find the speed of the wave. So it has a certain speed. Now, how can I find it? The wave speed is the wavelength divided by the period. I know that the wavelength is the distance traveled by the wave during one period. So wave speed is the wavelength over the period, and that's it. But there is a note here, is that in a homogeneous medium, it means when the medium, it has the same property at every point. So it looks all the same, okay? It's all water or it's all certain type of solid. The wave propagates at a constant speed, so it does not change its speed. Why? Because the medium is homogeneous. Now, if I want to put the above formula into a triangle, same thing we did with the previous triangle in the first chapter, right? You guys remember? This was the triangle, and to be honest, we can use it here as well. Okay, so if I gave you the distance traveled by this wave and during a certain amount of time, not the period, more amount of time. So if I gave you the distance that the wave is traveling, that already covered, during a certain amount of time, you guys can find the speed. Okay, but we have a specific one here where we have the wavelength, which is the distance traveled during only one period, and we have the period. So this is how we can find the wave speed, which is a meter per second. From this triangle, of course, we can find 3 formulas. where the speed is equal to the wavelength over the period. The period is equal to the wavelength over the speed, and the wavelength is equal to the speed times the period. Okay? Yeah, and that's it. So we're done with this chapter. It might be a little bit of a long lecture, but it's okay if we couldn't finish it this week. Of course, we're going to continue it next week. And yeah, so that is it. I hope you found this new chapter interesting. And if you guys have any questions, feel free to ask me anytime. Take care, and I'll see you when I see you. Take care, and bye-bye.